Hello, I will be covering the topic of traceability and security of dies in a chiplet configuration, in particular from a memory supply perspective. My name is Jun Kawaguchi, responsible for marketing for secure flash products at Winbond. Winbond develops and manufactures a family of secure flash products meeting different market needs. Secure memory products inherently needs to ensure security in the supply chain in addition to the security capabilities. Secure components, including memory products, will need valid and current security and supply chain certifications as a validation that the products purchased are genuine. Common criteria is a widely accepted international standard for computer security certification for products including semiconductors. For clarification, let us define the terminology. Traceability is an ability to trace the subject die back to specific production lots for purposes of manufacturer lot identification, production issue isolation, and other operational and manufacturing issues. In a conventional packaged IC product, traceability is achieved with a date code and lot code typically marked on the package. Some IC products may contain mask ROM code, which contains a version number. The device may also contain small non-volatile or OTP memory, which can provide traceability information. But what if a device contains a non-volatile memory, which is programmed during manufacture? This provides flexibility over mask ROM, but the topic of traceability extends beyond physical device to the programming code. In terms of ensuring the supply chain is secure for chiplets, we must have a mechanism to ensure that the die is genuine and not altered. A tampered die can either be counterfeit to save on cost or intentionally coded to cause damages. A semiconductor supply chain can be secured by working with reputable certification bodies and getting the proper certifications. Certification activity may involve documenting production flow, site audits, and ensuring that every touch point is identified and recorded. Such work is important for devices involved in financial security, such as the credit card security chips. Certification work is both expensive and time-consuming, and can be daunting for vendors that are not familiar with it. In addition to the physical supply chain security, programming of the devices need to be secured as well by a known and certified programming vendors. Any break in the supply chain can introduce risk factors. Consider that the chiplets contain devices from different suppliers manufactured in different factory and foundries, and with varying level of supply chain protection. A chiplet manufacturer will assume supply chain security for their subcontractors. This is similar to automotive industry, where car manufacturers ensure the integrity of their final product by setting and enforcing strict supply chain and production quality metrics through product part approval process, or commonly called PPAP. There are many more quality assurance processes in the automotive industry which we can learn to assure quality for chiplets. A well-known organization that validate, audit, and certify electronic system and supply chain is called Common Criteria. It is not a one certification vendor, but an established standard for which members strive to support. Interested suppliers should consult with their respective organizations. In terms of ensuring the supply chain integrity for the entire chiplet device, one method may be to catalog each chiplet ID information into a non-volatile memory for traceability. It is even more safer if the non-volatile memory contains a secure component so that the contents cannot be easily altered. You can make it as simple or as complex as needed. The tracing mechanism can be active, for example, tracking all failed or unusual booting and failures, or put in a counter limit the restart attempts. In this section, I will describe some use cases where non-volatile memory is used in a secure manner. Many systems require capability to update the firmware to keep systems current and close any security holes. In the past, the update may have been done manually, for example, bring a car to the dealership or send a USB stick to end user for self-update. For connected devices, much of these updates can be done over the air with no user intervention. There has been much improvement in managing the update method to prevent breaking the device, but I won't go into that topic here. The update needs security protocol to make sure that the updates are coming from authorized entity instead of rogue sites by validating signatures. The update itself needs to be delivered securely and validate the content is intact. Then comes the critical moment to flash the firmware and make the AV switch to restart the system with a new firmware. There are some key issues to address the over-the-air update schemes. One is a rollback protection, where a known vulnerabilities of older releases are not exploited. You may know that older OS versions of some mobile phones are available on the internet, and by reflashing to the older version, users can exploit the weakness and do something they are not supposed to do. That's the rollback. And you should also know that the next major OS version typically blocks a reflash to the older version, so that is a rollback protection. The system may keep track of update attempts, failed updates, and other actions to monitor system compromises. If the system can be restored to previous state, then adversaries can keep one hack, reset the previous state, try another hack, and so on, practically forever until they finally break the system. Monotonic counter is a one-way counter that cannot be reversed, and these replay attacks can be prevented. In addition to protecting the system, on-chip security can be used to enable subscription models for end product. A software-defined vehicle is a good example of it. Manufacturers can sell new car functionality as a one-time or subscription basis for the life of the vehicle. The feature should be enabled remotely to give opportunity for users to buy more functions in the future. Now, you certainly don't want to enable it to be easily accessible to end users, mechanics, or OBD scanner vendors online. You want to protect it. Described here is one of our proposals, but many schemes can be considered to ensure a secure enabling of functions post-sales. Likewise, you should be able to disable the function if users don't want to pay for them. In summary, we want to mention that the supply chain security is becoming an increasingly important topic for semiconductor suppliers. Matters become more complex for chiplets, with multiple dies from different suppliers are assembled together. Each supplier may have different assurance metric and a consistent methodology is needed for the market to accurately evaluate the integrity of the finished product. None of these are either cheap or quick. Cost, time, and expertise are needed to ensure the integrity of the complete solution. Also, connected devices will have over-the-air functionality, and you need to protect vulnerabilities relating to OTA functions. And finally, security schemes can be used not only to protect, but to enable new business models.